Hello everyone. My name's Eric. Thanks for coming to this session. I'm here to tell you today about our work on semi-symbolic inference. This is some work with our wonderful collaborators at MIT, IBM, and INRIA ENS. So the problem we're considering is streaming probabilistic programming. So imagine you want to write some state estimation code for a little two-wheeled robot, and the goal is to take in information from speed sensors on each of the wheels and use this to estimate the forward velocity and angular velocity of the robot. The thesis of probabilistic programming is that you should write down a probabilistic model of your robot in a programming language, and the programming language implementation should automatically perform Bayesian inference. What this means is that we're going to take the input values from the wheel speed sensors, feed this into the programming language runtime, and it's going to spit out a distribution that is conditioned on these random variables taking on these particular values. And the addition of streaming probabilistic programming means that this is going to happen over a sequence of time steps. So at each time step, we're going to take in some values from the wheel speed sensors and output a distribution that's conditioned on all previous observations. So our goal today is to try to implement such a programming language efficiently. So if you were going to write the code for this robot by hand, the thing you would want to use is something called a Rao-Blackwellized particle filter. And this is a long way of saying we want to combine exact probabilistic inference with approximate probabilistic inference. And the key idea in an RBPF is if we have some complicated distribution that we want to represent, we can represent it with a hybrid representation. So we'll have a sequence of particles, which are weighted samples, but then inside each particle is going to live an exact representation of a distribution. And the goal of combining this exact and approximate representation is to try and get the best of both worlds, because typically your exact distributions will have some sort of special case efficient operators, whereas your approximate representation can generalize to any distribution as the number of particles becomes very large. So in order to do this automatically, our starting point is some prior work that showed how to implement a probabilistic inference program using an RBPF. And the key idea here is to give non-standard interpretations for all the probabilistic programming operators. So when we say sample from a Gaussian distribution, we don't really mean draw a sample. We mean build up some sort of symbolic state that represents the random variables and their distributions, and when we have multiple sample statements, the relationship between the random variables. And as we continue on executing, this raises the question of what is a good symbolic representation. So one thing that we want is we want the symbolic representation to stuff as much information into the symbolic state, because typically the symbolic state, which is doing the exact part of the inference, is going to be more efficient. And at the very least, if the developer writes down something that looks like it should be able to do inference exactly, the programming language implementation shouldn't go ahead and approximate it if that's not what the developer is expecting. And then finally, there needs to be some consideration of overhead, because we're maintaining some sort of data structure with pointers at runtime. In this work, we present a particular symbolic representation where what we're going to be using are your standard symbolic expression trees that you might use to implement your language, or I think the next talk is going to cover symbolic execution. So it's a similar representation to that. And the key idea here is that the core atomic operator that you need to perform inference with this symbolic state is something called a swap. And what a swap does is it changes the dependency order between two random variables in your symbolic state without changing the overall distribution that the symbolic state is trying to represent. What we showed is that by using swaps to construct all your inference operators, we can prove a theorem which really gives developers a contract in the form of, if you write your program in a certain way, we can guarantee that the semi-symbolic runtime is going to perform exact inference in the places that you expect. And in our evaluation, we show that this matters because although semi-symbolic inference has a little more overhead than some prior techniques, on the examples where you really need these closed family theorems, you can get speedups because semi-symbolic inference is able to maintain exact representations, whereas alternative approaches have to fall back on approximate sampling. All right, so I want to dive into this example in a little bit more detail of a little two-wheeled robot. So this is a program for this robot written in the streaming probabilistic programming language ProbZelus, and I'm going to explain how this program is a model of the little two-wheeled robot. So In ProbZelus, the core objects are stream functions that take in streams and produce more streams. So the input streams here are L rate and R rate, which are the streams of input values coming in from the left wheel and the right wheel. And our output stream is a stream of distributions where each distribution in the stream is a joint distribution over the forward velocity vel and the angular velocity omega. This distribution is defined as follows. So we have some initial values for omega and vel, and then both of these are 0. And then at every time step, we specify that omega is drawn from a Gaussian distribution that is centered around the previous value of omega and has standard deviation 50. And just one remark that last omega usually refers to the previous value of omega, but at the first time step, it refers to the initial value 0. So there's a model for vel, which is entirely symmetric. And then we're going to specify what happens to the wheels. So this line specifies two things. First, it specifies that the left wheel is a random variable drawn from a Gaussian distribution that the mean is some linear combination of vel and omega and variance 1. And the second thing is that we're going to assert that we're conditioning the model. We're observing that this random variable is equal to the input value from the stream L rate. And this is going to condition all the variables on the fact that this variable equals whatever that input value is. And then there's a similar statement for R rate that just uses a different linear combination. So that's what the model is trying to specify at each time step. I'm now going to explain how this executes under semi-symbolic inference to actually perform the Bayesian inference that we want to do. So, as I alluded to before, when we say sample, we're not actually going to do any sampling. What we're going to do is we're going to build up our symbolic state. So we're going to make a new random variable omega that represents the new variable that we're sampling, and it's also going to store the distribution that it was sampled from in a manner that I think we might hear about in the next talk on symbolic execution. It's just going to build up the expression tree that says what it was sampled from. So vel is entirely identical. And now we're going to get to this observe statement. So the first thing that we're going to do is we're going to build this random variable that corresponds to the left wheel rate. And that random variable is L. And so two remarks here. One is that L has dependencies. So because V and omega appear in the distribution for L, we say that V and omega are parents of L. And I've drawn the parent-child relationship in black lines on the slide. And the second remark is that if you're at all familiar with Bayesian networks, that is exactly what we have here, is a Bayesian network with symbolic distributions. Yeah, if you're not familiar about Bayesian networks, don't worry, it's not essential for the talk. All right, so we've constructed the random variable for L. The next thing we need to do is actually perform the conditioning. And the way we're going to do this is a multi-step process. The first step is we want to turn L into a root node, and you'll see why in a sec. But what a root node is a node that has no parents. So we have to get rid of the parents. And the way we're going to do this is with swaps. Swaps. So a swap takes two random variables and switches their dependency order. So we're going to try to swap L with V and reverse that dependence. Why is this a reasonable thing to do? Well, we might imagine a simpler example. If we have some random variable x that's some Gaussian distribution and some random variable y that has mean of x, there is just a rule of probability called the conjugate prior rule for normal distributions that says that we can rewrite this model so that x has a complicated distribution that depends on y, and y has a distribution that doesn't depend on anything. So in our example, this situation is a little more complicated, but a similar type of reasoning applies. So the semi-symbolic runtime is going to determine that the mean of L is an affine function of the variable v. And then using properties of Gaussian distributions and affine functions, and also the conjugate prior rule for Gaussians, it's going to determine that the swap is possible, and that after swapping, the updated symbolic state looks like this. Similarly, we're also going to swap L with omega to get rid of that parent, and after doing so, the symbolic state looks something like this. So now that L is a root node, we can go to the next step of performing the observe, which is we're going to replace L's distribution with a delta distribution. So say that the current value of L rate is -1. We're going to replace L's distribution with a delta of -1. And this is just, the delta distribution is just a distribution with all the probability at one particular value. So one additional thing that this means is that in the other expressions, we can substitute -1 for L and partially evaluate them to simplify this. Once we do that, it looks something like this. And so at this point, we've accomplished the conditioning of the model on the fact that the random variable L is equal to -1. So we've completed this observation step. There's one more observation step, which I'm not going to go to in detail, but it's very similar and has similar effects on the symbolic state. And after we do that, this executes the first iteration of this stream function. At subsequent iterations, it's very similar operation. I'm not going to go into too much detail except to remark that the values of last omega and last vel refer back to variables that we've already encountered. So when we go to sample future values of vel and omega, we'll get v1 and omega1, which are random variables that have v and omega as parents. Okay, so I showed you how we implement sample and observe through this example. There's another semi-symbolic operation called value. And what value does is it instructs the semi-symbolic runtime to take a value that has an exact distribution and forces it to perform approximate sampling. So where does this come up? So in the example, I explained that the semi-symbolic runtime determines that this is an affine function. So a useful counterfactual is imagine if this was not actually affine. If there's a v squared in there, that means that there's no affine function that can represent this. The way semi-symbolic inference is going to deal with this is it's going to call value on the parent variable v. And what this means is we're going to draw a sample from the normal distribution that v was previously representing and replace v's distribution with a delta around that random sample. And so then using the substitution, we can simplify the inference problem that we're dealing with. But this comes at a cost of approximation error, because instead of having an exact distribution with v having a normal distribution, we now have this approximation. And we'll have multiple of these particles that in the limit approaches the right distribution, but this is not as good as having the exact distribution. So we would like to avoid this situation, or at least we'd like to understand when the semi-symbolic runtime gets itself into this situation. So in order to do this, we have a key concept called closed families. So a closed family is a set of symbolic states such that two things are true. First of all, if I try to swap any two variables in a symbolic state in the closed family, the swap is going to succeed in the sense that there will always be some sort of conjugate prior that it can exploit. And second of all, the resulting new symbolic state is going to be in the closed family. Classic example of closed family is the linear-Gaussian closed family. So if all your distributions are Gaussian and all your functions are affine, you are in the linear-Gaussian closed family. What is this good for? So closed families form the core of a contract that we can give between the semi-symbolic inference engine and the developer. So if you're a developer and you want to keep some set of random variables S symbolic, you can do the following. Ensure that all the variables in S are sampled from some closed family, and any variable not in S is specifically annotated to be randomly sampled using the value operation. And if you do this, we prove in the paper that the semi-symbolic runtime will maintain that no variable in S is ever going to be approximated with a random sample. All right, so this tells us circumstances under which developers can ensure that they don't need random sampling, and our evaluation shows why this is significant. So in these two graphs, what we're doing is we're increasing the number of particles, and you can see that the approximation error is going down, but the runtime, the time to execute, is going up. So to figure out how good these algorithms are, we can take a target level of accuracy that we want to achieve. And so we can see, sorry, it's hard to see, but the particle filter is in blue, and we can see that in order to achieve that target accuracy, it needs a relatively large number of particles and takes a relatively long time to execute. By contrast, semi-symbolic inference needs only one particle and can execute in a much shorter amount of time. So we did this kind of experiment across a range of benchmarks, and we evaluated against both basic particle filtering and some prior work on delayed sampling. And what delayed sampling does is it's very similar to semi-symbolic inference, but it uses a different symbolic state representation that it doesn't provide as strong guarantees as we have with closed families. And so sometimes it needs to approximate variables. So the benchmarks we used are a variety of benchmarks from prior work, and we also designed some benchmarks that are designed to exploit cases where you really need the closed family guarantee. And the results show that on the prior benchmarks, semi-symbolic inference has more overhead and so runs slower than delayed sampling. But on the benchmarks where the closed family guarantees are required, semi-symbolic runs faster because due to being able to maintain exact inference in these cases, whereas delayed sampling needs to fall back on approximate sampling, it can get better accuracy, use less particles, and run in a shorter amount of time. All right, so that's nearly all I have to say. I just wanted to briefly mention that there's some other related works in this area. There's a whole bunch of exact inference techniques that you might want to try to shove into a Rao-Blackwellized particle filter. So I think the short story is that compared to delayed sampling and semi-symbolic inference, it is less clear how to apply these in a streaming context. But I'm happy to talk more about these offline if you have your favorite exact inference methods. All right, so to summarize, I talked to you about semi-symbolic inference, where we use a symbolic state built out of expression trees. I explained the key operation, which is the swapping two random variables. I explained how we can use this to provide guarantees to the developer in the form of the RBPF guarantee, which uses closed families. And finally, I explained why this is important based on our empirical evaluations. And I'm actually a little ahead of time. So yeah, happy to take all your questions.
Give your mic,
Yeah.
and then use. You can use this one. So this one. I will use it too to say thank you for the talk. And yeah, please ask many questions. Otherwise, I will do.
Thank you. Thanks for the nice talk. I was wondering if you could comment on how this scalar symbolic notation relates to Gaussian process literature, in that you can kind of take like a multivariate Gaussian and represent as a big matrix, and also kind of related to that is have you looked at plate notation to like simplify those diagrams somehow, so you can kind of reduce the number of replication in the nodes? Thanks.
Yeah, so I can start with plate notation. So in some ways, it's almost a feature that these are always fully grounded Bayesian network-like things. It helps us.
Sorry, can you say what plate notation is?
Oh yeah, sorry. So the question was about plate notation, which is you can have basically more expressive versions of Bayesian networks that allow you to express whole sets of random variables on a single diagram. And I was saying it's almost a feature that we don't have this in our symbolic representation, because it allows us to do things like, if you have a set of random variables, you can specifically instantiate that set using the sampling-based portion of the code and have like 10 different literal variables instead of some plate that's trying to capture the 10 different variables. And then you can update them differently, and you can like flip a coin and get rid of half of them and things like that. And so we exploit that in some of our benchmarks. And so that's why we like to do that. And the other question was about Gaussian processes, which I didn't quite understand, because a Gaussian process is more like a stochastic calculus where you have a continuous space of random variables. Okay, all right, okay.
Hey, Eric. Yeah, thanks for the really interesting talk. I'm not an expert in this field, so feel free to let me know if this is like doesn't make sense. But I was just kind of curious, like this delayed sampling and semi-symbolic thing, are there like fundamental reasons why you couldn't maybe like fall back to one or the other, like combining the two, when you notice that maybe delayed sampling would be faster or semi-symbolic is like better in these situations?
No,
does that make sense?
That's a great idea. That totally makes sense, especially given the higher overhead of semi-symbolic inference. To be honest, I didn't think we expected that the overheads would be this high, but given that they are, I think it makes a lot of sense to try and do some kind of dynamic thing.
on, people. I will ask stuff. You were saying for the swap operation, you need to make the observed variable a root one, right?
I did say that.
Well, you said, let me say that again. When you observe a variable, you need to make it first a root variable.
Yeah.
But why do you do that? Because you were saying there's a relationship to Bayesian networks, and there you don't need to do that, right?
That is true. So the place where this comes up is our decision to implement conditioning as replace the distribution with a delta distribution. This step is only sound if it's already a root variable.
Okay.
So
this makes your representations then easier, or it makes it possible to represent it at all symbolic.
Yeah, I'm not sure. So like in a traditional Bayesian network, you would have some special annotation that like this node is going to get conditioned, and then update all the other distributions so that's consistent with this. I guess one feature of this is that the representation is more uniform, because after you replace it with a delta distribution, it's still just a normal Bayesian network. There's no special nodes or anything. It's just
So could you say this is kind of an operational semantics for a Bayesian network, where you do an observation and then the network changes a little bit, like a small step operational semantics thing?
I mean, you definitely could. There's always some equivalence between a Bayesian network and probabilistic program that you could exploit. I think I don't know. I think of this more as a relationship between conditioning and like interventions from the do calculus, where I think this is just one insight, is that you can think of conditioning on, if you have a variable that is at the top of your Bayesian network and you are conditioned on at some value, you don't need to worry about anything else. Just replace that distribution with a delta distribution. That is one. You can think of that as a special case of Bayesian network conditioning. The semantics of conditioning, I'm not sure I'm 100% clear on what the operational semantics of conditioning should be, but
Yeah, another question. I was kind of curious about this like closed family theorem. Does it ever make a difference when you have like two choices of swaps, which swap you apply first? Like, could you end, or is that actually what this theorem? Like, I guess in general, it kind of feels like you might have a choice between like what you can actually conjugate and what you can't.
Yes. Great question. So the closed family theorem negates this by being closed.
So you always end up with like a minimal thing after this.
So any swap that you do is going to keep you in the closed family. So you can keep swapping all you want. Your new state is going to be in the closed family, and you can still perform a swap on any two variables.
But could you like, depending on what you choose, the order of swaps you choose, end up with like two different final?
You can certainly end up with two different final symbolic states.
Yeah.
But both symbolic states will be in the closed family.
And are they like equivalent in terms of efficiency and all the things that you want from?
They are not. So yes, I think there's two things to separate out. So one is that the closed family doesn't care about what order you do the swaps in, because you're always going to stay inside the closed family. But there are other things that do. So one thing I didn't have a chance to get into is we have this function called hoist, which decides which order to do the swaps in. And there are multiple swap orders, and it does matter for things like efficiency, or if you're not in a closed family, you can wind up having to introduce extraneous approximate sampling operations. So I think it would be really cool to understand these swap orders more, especially in relation to other problems in probabilistic inference.
Cool, thanks.
Sure.
I didn't quite understand. Sample and value do kind of the same thing, but not really. Is that true? Sample says, well, now this variable is distributed according to this distribution, and value actually takes a sample, or is that not really correct?
Yeah, that is correct. I think that's another thing I didn't get too much into is the reason why they originally called it delayed sampling is because you're effectively doing the sampling lazily.
Mm.
Instead of drawing the sample right away, you're delaying it or lazily doing it at
And
some
then
other
the
point.
programmer can say when to do it. Like this
Yes.
value is right.
And yeah, and the right answer when to do it might be never, hopefully, if you can stay exact forever.
Okay, cool. Let's, unless there's no more questions, let's thank Eric again.